Hello, everyone. Thank you very much, Jim, for introducing me, and to you all for joining this presentation. My name is Ryan Bergeron, and I am a GE specification engineer located in Minneapolis, Minnesota. I am honored to have this opportunity of helping you apply the new 2017 NEC, National Electrical Code, Article 240.67, Arc Energy Reduction Paragraph for fuses 1200 amps or higher. This will be applicable for the new electrical safety requirements for any facility adopting the 2017 NEC, such as commercial, industrial, data centers, or healthcare type facilities. This is an opportunity for GE Industrial Solutions to partner with EasyPower along with consulting engineers and end users about increasing the awareness of this new paragraph adopted in the 2017 NEC code cycle. Thank you again to EasyPower for this opportunity. There is a bigger picture of why we are discussing the 2017 NEC code. I will offer a set of 3 statistics during the course of this presentation to help you understand why arc energy reduction is important for fused power distribution systems. It is my privilege to help educate those who attend the session, walk away with a quality PDH credit, as well as help educate others. Specifically, this presentation will help you understand the importance of arc energy reduction for fuses in terms of the new arcing current clearing time requirement, along with several methods to reduce arc energy for fuses in a power distribution system. To be clear, this presentation will not provide any live EasyPower software demonstrations. Please feel free to contact EasyPower and feel free to ask them for any technical assistance. Copyright materials. This educational activity is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of this educational activity without written permission of the presenter is prohibited. Copyright GE Industrial Solutions 2018. GE Industrial Solutions has given permission to EasyPower to reproduce and distribute this presentation. Disclaimer: this presentation does not purport to be an aid or instructional tool with respect to the matters shown in the presentation material, but rather it is only to be viewed as illustrative of certain types of services offered by the General Electric Company and its affiliates. The General Electric Company and its affiliates, 1, accept no liability of any kind, including claims for bodily injury or property damage, which may arise from the use of or work undertaken on the basis of this presentation, and 2, make no warranties or representations expressed or implied with respect to the accuracy, completeness, or use of the information contained in this presentation. The customer hereby identifies and holds harmless General Electric Company and its affiliates from any such claims. If you attend or listen to this training, you agree to the limits stated herein. Purpose: this session will provide you with power distribution system information on fuse over current design options to protect a single medium voltage bus, a transformer asset with a primary bus and a secondary bus, and a single low voltage bus that provides both a high degree of reliability, coordination, and selective coordination in combination with minimizing arc flash energy for electrical safety. The application examples in this presentation involve specific properties of electronic devices with fuses for arc energy reduction that meet the 2017 National Electrical Code. Learning objectives. At the end of this presentation, you will be able to, number 1, state the conditions used in power distribution system applications with fuses and varying cable lengths that impact arc flash energy. Number 2, explain how a composite instantaneous time current curve is applied to protect a single low voltage bus for a fused distribution system. Number 3, describe how to protect a single medium voltage bus and a transformer asset by using a differential relay for arc energy reduction with a service entrance fuse switch. And finally, number 4, explain how a composite instantaneous time current curve is applied in maintenance mode to protect a single low voltage bus for fused distribution system. The agenda for today will be discussing covers items covered within this technical session include item number 1, provide an overview of fuses and electrical distribution. Item number 2, review the 2017 NEC 240.67 article. Item number 3, show the presently adopted United States 2017 NEC map along with another page showing the pending adoption map available on the NFPA website. And finally, number 4, provide application examples for the methods to reduce clearing time. As fuses were first patented on October 14, 1890, they have been utilized for various voltage levels of electrical distribution. Fuses have been used as overcurrent protection devices in 15 kV and below power distribution equipment in switchgear, transformers, low voltage switchboards, and panel boards. Thousands of design iterations have evolved from the metal strip or fused wire element. The I²T rating is related to the amount of energy let through of the fuse element as it clears the electrical fault. Current limiting fuses have been introduced to operate quickly, where they limit the total let through energy that passes into the circuit, helping to protect downstream equipment from damage. Throughout the course of time, up to 2013, the fuse is safeguarded from bolted faults. The electrical distribution industry was providing with an industry-leading electronic device in 2014, which provides significant arcing current reduction for fuses. Prior to the 2017 NEC code, there was no enforcement of any type of arc energy reduction for fuses, and unfortunately, arcing faults have still led to accidents, fires, and sometimes tragic events. The 2017 NEC code has been adopted by several U.S. states and has begun to enforce and take the next step to solve arcing current problems for fuses. The first statistic comes from the NFPA website link provided on this slide on the right-hand side. Please refer to page 99 of the NFPA PDF, Table 8.A, non-home fires involving electrical distribution equipment or lighting. In the time period of 2010 to 2014 of the annual averages, wiring and related equipment equal to 59% of those fires. And transformers and power supplies also equated to 13% of those fires. So adding the two numbers for wiring, transformers, and power supplies, which accounted for 72% of the fires during this 4-year time period. This presentation will begin to address various areas where arcing faults occur in electrical power distribution system for fuses. The first example of an arcing fault between the 15 kV fuse switch and the transformer primary. If busway or cable connections, top exit, side exit, or bottom edge exit between the 15 kV fuse switch and the transformer primary are utilized, during these arcing fault events, the hazard zone consists of a 3-dimensional area around the fault shown here. The second example of an arcing fault between the transformer secondary and the primary low voltage fuse switch. If busway or cable connections, top entry, side entry, or bottom entry shown here, between the secondary side of the low voltage transformer terminals and the fused low voltage primary in the main section are utilized, and during these arcing fault events, the hazard zone consists of this 3-dimensional area around the fault shown here. I'm illustrating a separation between these sections to help show where arcing faults can occur. But it is commercially possible to close couple these sections together if space constraints are present. If you do have closed coupled 15 kV fuse switch substation application, changing the length of the cables, changing the impedance of the unit substation, but the arc flash zone will affect the entire substation, just like the first example. If an arcing fault occurs on the closed coupled unit substation, it would significantly and immediately affect the entire substation with the large arc flash zone. But for this illustration, I'm showing a separation. The third example of arcing faults between a primary as well as a secondary side of the low voltage fuse switch or branch section. If bus bar or cable connections between the primary or secondary side of the low voltage fuse switch located in the main section and the fused low voltage branch section are utilized, During these arcing fault events inside the distribution section, an arc can propagate and ricochet inside these sections and affect the immediate arcing current hazard zone within this three-dimensional area on the low voltage side. The goal of the 2017 NEC 240.67 arc energy reduction paragraph for fuses will begin to address and solve these arcing current problems for 15 kV below equipment from the utility line side to the point of load. This webinar will focus on topics that help advance technology for humanity, which is the mission and vision of IEEE, Institute of Electrical and Electronics Engineers, for continued improvement. Let's review the code on the subsequent slide. The NEC is taking additional steps to solve the arc flash problem for fuses and increase safety for several types of facilities. In GE's collaboration with consulting engineers, end users, and EasyPower will hopefully reach a broad network. In general, electronic devices for fuses on any system 1000 volts or less are being introduced to help reduce arc energy for fuses per the following means. The items highlighted in gray are newly introduced items for 2017, which represents this entire article for fuses in the codebook. The first section, 240.67, where fuses rated 1200 amps or higher are installed, 240.67A and B shall apply. This requirement should become effective January 1st, 2020. Paragraph A, documentation. This involves time current curves, which are available on specific manufacturer websites for specifiers. Paragraph B, method to reduce clearing time. In this paragraph, please notice that the NEC is specifying that a fuse shall have a clearing time of 0.07 seconds or less at the available arcing current, which would represent the instantaneous region of the time current curve. B1, differential relaying or bus differential. B2, energy reducing maintenance switch, or in other terms, a maintenance switch. B3, energy reducing active arc flash mitigation system. This presentation will not discuss this option in detail. In the future, it may be commercially possible to provide information about the improvement of arc flash relays that monitor and react to pressure, light, and/or current from an arcing event in a low voltage system. This presentation will provide specific application information for the items in A, B, B1, and B2. B4, approved equivalent. The State Electrical Inspector, or AHJ, authority having jurisdiction in your local area, may approve of a different method to reduce arc energy for fuses 1200 amps or higher. These application examples provided in this EasyPower session will revolve around the existing IEEE 1584-2002 standard for arc flash calculations. IEEE presently has a 1584 working group updating the arc flash equations, which you can receive updated information from the IEEE website. IEEE is the owner of the arc flash calculations in partnership with NFPA, OSHA, etc. Again, this presentation is based upon the IEEE 1584-2002 arc flash equations. Here is a picture of the 2017 NEC map, and there are 19 states that have adopted the new code. In addition, the NFPA website link is provided at the bottom of this slide. On the left, there are references to at least 6 code references for coordination, which typically refers to the 0.1 second and above region in a time current curve. Please check with your local AHJ about what time interval is required to meet this code requirement, as the NEC doesn't specify the time interval. In addition, there are references to at least 8 code references for selective coordination, which typically refers to the 0.01 second selective coordination in the instantaneous region of a time current curve. Various manufacturers have public data available today, as modern technology has made it possible to selectively coordinate to 0.01 seconds for power distribution systems. Again, please check with your local AHJ about what time interval is required to meet this code requirement, as the NEC doesn't specify the time interval. It is a requirement of the consulting engineer to specify this time interval for 0.1 seconds or 0.01 seconds in their bidding specifications for the state, local, and NEC requirements. GE's selective coordination website and GE's time current curves for our devices are provided as links on the left that comply with the documentation requirements of the NEC. Here is a picture of the 2017 NEC pending adoption map, as there are 13 states in the adoption process cycle. So over 60% of the United States is taking measures to review the new 2017 NEC code and potentially adopt it. Again, the link to the NFPA website is provided at the bottom of this slide. This is an IEEE 1584 arc flash incident energy chart that utilizes the incident energy, calories per centimeter squared on the y-axis versus the short circuit current available on the x-axis. As you can see, there are two diagonal lines represented within the chart, such as at a low voltage service entrance application. The light green line drawn in that chart in the center is an instantaneous electronic device for fuses clearing at 0.058 seconds, or 58 milliseconds. The dark green line drawn in the center of the chart is a device with an electronic maintenance switch with a clearing time of 0.05 seconds, or 50 milliseconds. How to read this chart. When there is an arcing event at approximately 42 kA, which is labeled with an orange arrow, and using the IEEE 1584-2002 arc flash equations, you will follow the bottom of the orange arrow from the x-axis up to the diagonal line, which represents the clearing time of the electronic device, and you follow it horizontally over to the left, which represents the y-axis, to estimate the incident energy level of approximately 4.5 calories per centimeter squared. This would be an electronic device that is turned on, measuring and clearing to any arcing currents in the low voltage distribution system at a service entrance location for fuses, which GE's HPC2 second generation high pressure contact switch meets this requirement for the 2017 NEC code for fuses. The HPC2 is an electronic device for overcurrent protection for the low voltage main device with Class L fuses. During maintenance mode, GE's term is RELF, or reduced energy let through, which is a component with a blue LED switch that is turned on either manually or electronically. During an arcing event at the service entrance location, you will follow the bottom of the orange arrow from the y-axis up to the diagonal line, which represents the clearing time of the electronic device, and you follow it horizontally over to the left, which represents the y-axis, to estimate the incident energy level of approximately 3.5 calories per centimeter squared. The GE HPC2 device with the maintenance mode turned on meets the 2017 NEC requirement per 240.67V2, which clears an arcing fault within 0.05 seconds. Again, this is a temporary feature with Class L fuses at a service entrance location. As a side note, please remember that if a person unfortunately witnesses a plasma burst of energy of an arcing event of 1.2 calories per centimeter squared, it is enough energy, along with the copper or aluminum shrapnel, that would travel with an explosion where a person would experience a second-degree burn along with potential hearing damage if no PPE or personal protective equipment is worn around a power distribution system. Please take every precaution to always uphold electrical safety and wear proper PPE as you enter and work on energized equipment in electrical rooms. The next slide will be an apples to apples engineering analysis of why the arcing current clearing time is important for fuses. Here is a screenshot of a low voltage motor control center example based upon the IEEE 1584-2002 arc flash equations. This example of this apples to apples analysis for fuses consists in this system as there are two upstream 400 amp fuses. These fuses protect two equally sized 200 horsepower motors downstream. The only difference is, on the left, there's a 10-foot cable with an arc flash and some energy label of 0.6, calories per centimeter squared. Now on the right, there is a 600-foot cable. Please notice the higher arc flash incident energy label on the 600-foot cable length of 1.6 calories per centimeter squared. Let's understand why there is a higher arc flash label with the 600-foot cable length on the subsequent slide by looking at the arc flash analysis report for fuses. From the arc flash report highlighted in red at the upper left-hand side of the screen, notice that the trip time window that is enlarged and shown in the center of this slide shows the 10-foot cable with a 400 amp fuse with a clearing time of 0.015 seconds, and the 600-foot cable that has the same upstream 400 amp fuse clearing at a different time interval of 0.133 seconds, which is just under 10 times longer to clear, which represents the arcing time, or T-arc, in line item number 4 in the equation, is an input to the arc flash incident energy equation on the upper left-hand corner. The arcing current clearing time requirement is the standard in the 2017 NEC 240.67 code, as the paragraph specifies 0.07 seconds or less for fuses 1200 amps or higher. This slide is provided as an engineering analysis. There are two important equations that are shown on the slide that we know of today. Incident energy is equal to 0.1 times the system voltage times the I-arc, or the arcing current, times the T-arc, or the arcing time, divided by the distance squared. Secondly, the I-arc, or the arcing current, is equal to 0.29 to 0.79 times the voltage fault. Arcing faults can range from 29% to 79%, which could change in percentages based upon various power distribution criteria for the standards in the modeling software programs you are using. In this clearing time example for fuses, the 10-foot cable with the arcing current trip time, noted as the arcing time, or T-arc, has the influence on the arc flash incident energy label from the arc flash analysis report with a corresponding clearing time of 0.015 seconds, which reflects the lower arc flash label of 0.6 calories per centimeter squared, shown on the right. The 600-foot cable with the arcing current trip time, noted as the arcing time, or T-arc, has more influence on the arc flash incident energy label from the arc flash analysis report, with a corresponding clearing time of 0.133 seconds, which reflects the higher arc flash label of 1.6 calories per centimeter squared, shown on the bottom right. Now that we have completed an engineering low voltage arc flash analysis for fuses with different arcing current clearing time examples being extremely important for fuses, let's begin to apply the 240.67 code for paragraph B. Reviewing the basics of a time current curve, LSI, which refers to long time region, short time region, and the instantaneous region, which are drawn on the left. Reducing the time component, which is labeled on the y-axis, is a key aspect to lowering the arc flash incident energy level. As demonstrated on the previous slide, the two 400 amp fuses with the 10-foot cable length versus the 600-foot cable length had different arcing current clearing times. As the NEC is specifying an arcing current clearing time of 0.07 seconds or less, this red line represents the specific clearing time in the instantaneous region of the time current curve by the new 240.67 NEC code. A time current curve like the one shown here can be achieved through a composite time current curve clearing in the instantaneous region of the time current curve, which is demonstrated here for both arcing faults, protection provided by the switch, and voltage faults, protection provided by the fuse. In the lower band is a minimum switching device commit time that has begun to measure the arcing current fault event, or also known as the initiation point. The upper band is the maximum clearing time, which clears the arcing current fault at 0.058 seconds. The orange arrow shown here demonstrates the 42,000 amp default clearing at less than 0.07 seconds. Again, the electronic device utilized in this EasyPower presentation is GE's HPC2 device that meets the 2017 NEC 240.67 requirements for A, documentation, B, device having a clearing time of 0.058 seconds, and B2, a maintenance switch. The HPC2 meets the arcing current clearing time requirements of 0.07 seconds or less. HPC2 time current curves are available on the GE Industrial Solutions website with integral ground fault, as this device is intended for both normal or forward power distribution as well as reverse applications such as distributed energy resources. In the Specifications tab on the left, the electronic device shown here would be adjusted per the appropriate trip settings to achieve coordination and/or selective coordination per the NEC requirements in a low voltage power distribution system. In the Phase Trip tab in the center, the instantaneous pickup is highlighted in the red box. A pull-down menu is available from some software programs to help adjust the instantaneous pickup settings, which allow for proper coordination and/or selective coordination, along with meeting the specification clearing time requirement of the 240.67B paragraph. The instantaneous pull-down menu allows the time current curve to be moved from the left with a value of 2.0, ultimately to the right at a value of 10.0. If the time current curve settings need to be adjusted, then the pull-down menu can be utilized to move the time current curve from the left to the right with a maximum value of 10.0 to achieve proper coordination and/or selective coordination while clearing arcing faults per the 240.67 requirements of the 2017 NEC. Right below the instantaneous pickup is GE's route that can be checked on in this Phase Trip tab. GE's term that stands for Reduced Energy Let Through for the maintenance switch per 240.67B2 defines the pickup value in this section of the modeling software. For plotting the fuse on the right-hand side of the screen, you can select to plot the time current curve for the fuse type per the EasyPower menu options available in the software modeling application. The Specifications tab on the left-hand side. A person will create a base kV of 0.48 or 480 volts, in this case for a switchboard application demonstrated here. In the Arc Flash Hazard tab on the right, notice the Orientation pull-down menu. Notice that the default is vertical, which refers to the bus orientation in any piece of electrical equipment. Utilize this new EasyPower pull-down menu for the appropriate bus orientation for your distribution application, such as in switchboards and/or switchgear. With the instantaneous pickup range pull-down menu available, such as in this case, as 2.0 is selected on the left-hand side of the screen in the pull-down menu available, which is adjustable from 2.0 to 10.0 for coordination and/or selective coordination purposes. The instantaneous pickup value of 2.0 is labeled on the green screen off to the right. Please notice the specified clearing range of 0.07 seconds is again clearly labeled per the NEC requirements, with the lower and upper clearing time bands marked per the composite instantaneous time current curve shown in the center of the page. On the left, protection provided by the switch, and on the right, protection provided by the fuse. From the instantaneous pickup range pull-down menu, with adjustability of 7.0 being selected as the instantaneous pickup value, which is also shown on the green screen on the right. Again, the setting shifted the composite instantaneous time current curve from the left to the right as the pickup was increased from 2.0 to 7.0 and still meeting the 0.07 second arcing current clearing time requirement by the electronic device. The results from the Arc Flash report are as follows. In the bottom right-hand corner of the screen, it shows a clearing time of 0.058 seconds, which is the result that meets the new 2017 NEC 240.67 specification arcing current clearing time code requirement for fuses, which is the solution we are looking for. Please notice the informational note number 3 in the center of the page. The IEEE 1584 reference is mentioned here as it is one of the available methods that provides guidance in terms of determining the arcing current. Various arc flash software programs illustrate arcing currents differently, which in this case, a red vertical transparent arcing current line in the middle of the page has been manually added with the maintenance mode turned on. Different voltages across North America will change the position of the arcing current, moving it from the left to the right, as it is up to the qualified professionals to obtain the appropriate settings of the power distribution system applications. In a different slide, I will demonstrate an application that will model the routes, reduce energy let through, maintenance mode turned on for the 240.67B2 maintenance switch application. For now, let's move sequentially through the 2017 NEC code, where the application for B will be discussed next in a typical fused power distribution system. A second statistical anecdote noted on page 109 of the NFPA PDF that was presented earlier. Table 8.7, non-home fires involving electrical distribution equipment or lighting. From the time period of 2010 to 2014, annual averages. The first line item highlighted within that report is mentioned as electrical wire or cable installation, which equated to 38% of those fires during this time year period. These statistics are extremely relevant as the NFPA data correlates to the application examples presented in this webinar and specifically in this slide. For 240.67B, the instantaneous device, during an arcing fault with the red X shown here, the electronic device would measure and clear the arcing fault event shown here and provide load side arc energy reduction for this section of the low voltage distribution equipment. This device protects and affects the arc flash instant energy label of everything inside this zone, including the entire main section and branch section, such as a switchboard application. Next is the differential protection principle, which is accomplished by a sophisticated 87T transformer protection relay available from several manufacturers. The details of high and low impedance bus differential will not be discussed, but it is the intention of this presentation to briefly discuss an application example per 240.67 code and of an 87T protective relay to help prevent the following fault types: phase-to-phase faults, three-phase faults, ground faults. Item number 4 would be core faults, which refer to the winding insulation of the transformer core. And finally, tank faults, which refers to the clearing of internal faults that would break an oil-filled tank, leading to a large fire. In the center of this slide, under the protected zone, as I1, or the current entering into the zone of the transformer, plus I2, the current leaving the transformer zone, is equal to 0, then you would have a no fault condition with this differential protection principle. On the right-hand side, there would be a protected zone if the current from I1, current entering into the transformer, plus I2, current leaving the transformer zone, is greater than 0. If this were to occur, then there would be a fault conditions, but the 87T would clear the fault with this method. Again, transformer differential protection, 87, compares the current going into the transformer zone against the current leaving the transformer zone. Again, this presentation will not go into the details of protective relaying, such as 87T, 5051 protection examples, settings, etc. Please refer to the protective relaying presentations for full explanations of the 87T phase-over current grounding from other professionals within this industry. This presentation has 2 slides dedicated to briefly discussing application examples around 240.67 B1 bus differential for fuses. Let's review the application example next per B1 of the 240.67 code. 240.67 B1 bus differential. This method requires access to the 15 kV switchgear, as the primary disconnect for this application requires a set of contactors that are cycled to clear the downstream arcing fault, such as a medium voltage upstream circuit breaker. During the various forms of arcing faults documented on the previous slide, the transformer protective relay with the 87T function, along with current transformers, along with retrofitted CTs, are included as examples in the main section. In this slide of the low voltage distribution section, a protective relay is measuring and clearing these arcing current events between the medium voltage switchgear and the low voltage CTs, located just ahead of the primary fuse switch in the main section in the low voltage distribution section. The third statistic, noted on page 107 of the NFPA PDF in the link provided earlier in the presentation. Please refer to Table 8.6, Non-Home Fires Involving Electrical Distribution Equipment, or FIDE. From the time period of 2010 to 2014 of the annual averages, the area of origin in the first line item mentioned in Table 8.6 is noted as switchgear or transformer vaults. Again, this is the area of origin for switchgear and transformer vaults, equaling 7% of the fires during this 4-year time period. Again, it is the intent of this presentation to help those who attend to not only walk away with a quality PDH credit, but also to help educate others with these statistics as application examples to help coach others who need help with electrical safety and obey OSHA safety standards. Advancing technology for humanity is the purpose of IEEE. The purpose of this slide is to provide both line and load side arc energy reduction for this area. The protective relay would not pick up any arcing faults downstream of the CTs, which would be located physically above the CTs in the main section. Please refer to 240.67b and b2 for the arc energy reduction examples provided in this presentation. The overall general practice or rule of thumb for a main switchboard section is to add roughly 5 inches of depth for line or load side transformer differential CTs that are drawn here. The CTs may have to be placed within the low voltage main fuse switch line side to leave some part of the line side unprotected by the fast 87T between the CTs and the switch. If the CTs can be placed on the load side of the low voltage main fuse switch, which is just above the switch in this picture, it would provide the optimal zone of protection. Every part of the line side will have the high-speed protection of the transformer differential. The placement of the CTs connected to the protective relay in the low voltage fuse main section needs to be carefully considered to meet the 240.67 code requirement. For the medium voltage overcurrent protection device, a circuit breaker contained in a metal enclosed switchgear or metal clad switchgear can be utilized for this application with a protective relay. The upstream devices, such as a 15 kV circuit breaker, can be powered down from the line side to perform maintenance on the entire de-energized downstream equipment. Modern medium voltage vacuum circuit breakers of today offer typical operating speed of 3 cycles. Operating mechanisms are less complex and easier to maintain, and various manufacturers offer embeddable design that eliminate leakage caused by mechanical impact and provide maximum protection to the vacuum interrupter from moisture and dust. The application of 240.67b2, the maintenance switch. It is very important to note that this is a temporary setting as a service entrance location per IEEE 1584-2002, which is highlighted in the yellow box in the upper right-hand side of the screen. As qualified professionals are performing maintenance on the low voltage distribution equipment, in the event of an arcing fault, the electronic device will measure and clear the arcing current event and provide load side arc energy reduction for this low voltage power distribution section. Please notice that the clearing time represented in the beginning portion of this presentation had a diagonal green line drawn at 0.05 seconds, or 50 milliseconds, per the IEEE 1584-2002 arc flash equations in the arc flash instant energy analysis slide. At the bottom right-hand corner of the screen, the 0.05 second clearing time is shown as the arcing current clearing time for this fused application. On the left-hand side of the screen, notice the device settings for routes for reduced energy let through is turned on at 1.5 with a pickup band value with the blue LED switch activated just below the green screen on the left-hand side. Remote activation is possible as well. In the modeling software program, please take your mouse and hover it over the GE 1600 Class L 1600/1600A or amp device in the center. Right-click your mouse and move your mouse below. Hover it over the maintenance mode. Move your mouse slightly to the right. And finally, left-click to turn on, which would apply the instantaneous settings previously shown as 2.0 or 7.0. With the route switch turned on and applying it, it turned on a blue LED light, and the electronic device moved the GE HPC2 time current curve to a lower time interval of 0.05 seconds, as is required by the 240.67B2 code. The clearing time example noted in paragraph B had a clearing time of 0.058 seconds, but in this slide, the clearing time of the 0.05 seconds is labeled on the bottom right-hand side. To achieve the 0.05 seconds, please refer to the green screen off to the left as the setting of the route with a pickup of 1.5 being selected. Again, this 1.5 pickup band temporarily lowers the arc flash energy during an arcing current fault event on the load side of the low voltage power distribution section. To be clear, this route feature is not intended for permanent use, as coordination and selective coordination will be compromised if there is a downstream fault that could lead to a power disruption. Please notice that the arcing current is a vertical transparent red line shown in the center, and the pickup band is off to the left. An extreme hazardous condition could be witnessed if the arcing current directly overlays the pickup band. In other words, the red transparent line of the arcing current in the center is directly over the purple pickup band of the time current curve on the left, which is why experience with time current curves are necessary, as arcing faults can range from 29% to 79% of the bolted fault value in low voltage power distribution systems. Legal supervision as well as experience is required per the NEC language. I will highlight this language on the next slide as one of the notes. The first summary point in the maintenance mode, which again is highlighted in yellow in the upper right-hand corner, which meets the requirements per the 2017 NEC Article 240.67B2. The first line item is that it is intended for temporary application. Second line item is that it is an instantaneous setting on the trip unit device. Line item number 3, when enabled, it creates or increases the overlap with downstream devices, reducing both coordination and selective coordination per the NEC requirements. Line item number 4, it requires user intervention to enable the arc energy reduction. And finally, line item number 5, an arc energy reduction is only realized if the maintenance mode pickup band is below or to the left, which refers to the purple vertical line, and not overlapping the arcing current range, which is the red transparent line. The application of 240.67B2, the maintenance switch, this method requires low voltage access to the load side main section distribution, which are bottom or top entry, noted here, of the equipment that can clear the arcing current requirement within 0.07 seconds or less for fuses. If an arcing current event occurs at this location, with the red X drawn here, the electronic device will provide load side arc energy reduction for the power distribution section in this application. To help summarize this presentation, line item number 1, the 2017 edition of the NEC requires arc energy reduction method to be used on fuses 1200 amps or higher by January 1st, 2020. Line item number 2, reducing arc energy requires fast clearing at the arcing fault amperages, which are less than the bolted fault amperages. Line item number 3, maintenance switching is a temporary measure that requires user intervention to enable the arc energy reduction. And line item number 4, having a maintenance mode in itself does not necessarily reduce arc flash energy, as the trip units must be properly set in relation to the arcing current. This concludes the technical content of this presentation.